What liquid do you think has a lower specific heat and why?
Acetone.
Acetone, it does.
Because the temperature increased more quickly and it boiled easier.
Good. So the liquid that increased in temperature more quickly, even though both this is the cool thing about chemistry. I think the cool thing about science and specific heat. I just think it's a pretty cool concept. It's not even a concept, but a thing. Both liquids were given the same amount of heat, but only one of them heated up much faster, and that was the acetone. And what Marcy said is good. It's a good answer. Acetone specific heat is 2.15. Water is 4.18, right? So you don't have to write this, but water is 4.18, acetone is 2.15. So that means if I have 1 gram of water, it takes that much energy to raise it 1 degree. If I have 1 gram of acetone, it takes almost half as much water to increase that same amount, right? So water is going to heat up almost twice as slow. It didn't really appear that way, but what would have happened is obviously the acetone was boiling, the water would still continue to get hot and hot and hot, and it would take a while to reach 100 degrees, and that one was already boiling at 55 or something like that. So, yeah, what she said was right on the money. Whatever substances in this world heat up very quickly have very low specific heats. Any substances that heat up slow have high specific heat. So that's a good answer, and I hope a lot of you wrote the same thing. But let's talk about why. Now, the regents probably will never ask you this, but I like to ask questions like this sometimes. Why? Why does water have a higher specific heat than acetone? You already know something about those two liquids that is very different. I'll give you a hint. Propanone on table H is acetone. So remember on table H, you have those 4 liquids. So propanone is right here. That's the acetone. That's acetone. And water, I think, is the third one. Here's H2O, right? And then there's the dotted line. So that gives you a little hint as to why water has a higher specific heat than acetone. That is evidence of the answer I'm looking for. Which one? Acetone has weaker forces of attraction. So what causes temperature to increase? The molecules moving, the kinetic energy. Very good. So let's think about this. If this liquid has strong forces, what does that mean? It means the particles kind of want to be closer together, not moving as much because they're attracted to each other, right? They're not free to move. These particles in acetone are more easily movable, can move easier because they have weaker forces. That's why it evaporates so quickly. So it should make sense to you that if you're giving both of them the same amount of heat, the one with a greater force will take longer to break or weaken those forces so the particles can move fast, which increases temp. The ones with weak forces can start moving quicker, faster, because they're held with weak forces. They're held loosely. So that's really why specific heat of the liquids is different. However, it gets really confusing with solids and metals, so that metal pot has stronger forces than water and acetone, but it has a specific heat of like 0.8 or something like that. So what is that about? How come metals, even though they have really strong forces, will have a really low specific heat? The liquid makes sense. The forces of attraction make some sense. What about metal? Why metals? Why would they have really low specific heat and heat up really fast? They have really strong forces. Metals are very strong forces. So that whole forces of attraction thing kind of goes out the window. There's an advanced answer. If you take AP Chem, we'll talk about it. It's confusing even for me. Although, yeah, like half of it is confusing for me. It's confusing. So we're not going to get into that. But what are metals good at doing? conducting heat. So metals, the way that their particles are arranged and how it's bonded allows it to conduct heat and electricity very well. That's the short, easy answer to explain it. That it has a really small specific heat or low specific heat because the way the particles are bonded and attracted to each other in a metal, it allows for heat to conduct or heat to transfer through it very quickly. And that's the best I can do right now because you have to learn a whole bunch of other stuff first. So AP Chem, we do talk about that. It's actually a new kind of unit in there. But anyways, that's not a regents thing. But the concept is anything with a high, so regents concept here, high specific heat means it heats up slow, cools down slow, heats up fast, cools down fast, the lower the specific heat. All right? So that's an important concept to understand, I think. Besides just doing these calculations and using a calculator, getting answers, understanding what you're doing, right? So that's important to me that you understand a little bit more. Okay, let's go over these 3 problems. I was going to have you come up here, but I'm going to speed it up a little bit. Can anybody show me or tell me how to set up number 1 on that sheet here? Go ahead.
Q equals 40 grams.
Q equals 40
Times X.
times, can't be X, because you already gave me an X. Q, Q's my 4.18, right, specific heat, because this is water, right?
Yes.
Yeah, and then the change in temperature? 20, positive or negative?
Positive.
Positive, so it's being heated,
Yep.
right? So your initial temp was 10, your final temp is 30. It's always final minus initial, 30 minus 10. So 40 times the specific heat of water, that doesn't change, it's on table B, times 20, multiply those together. I didn't give you any rules for rounding or anything, so probably keeping the tenths. I don't think the top says anything. You could do significant figures. 40.0 has 3, 4.18 has 3, and 20.0 has 3. However, I think our number is going to be too big for 3. It makes it weird. Laura, did you get this?
3,344.
3,344 joules. Is this endothermic or exothermic? Kira, how do you know?
Because it's all negative.
Good, it's positive. Here's the other way you know. The question says heated. So if you give water heat, it's gaining the heat, increasing in temperature. That means it's absorbing heat, right? Endothermic. Okay, 6 we'll do last. Number 7. Who wants to tell me how to set up number 7? Mariana, thanks for volunteering.
30,
Well, I'm going to do Q equals, because that's what we're looking for.
30
Yep.
times 0.899
0.899, sorry, yep, 0.899.
times 20.
Times what?
20.
20. Good.
She owes me 2 refined cheap.
Where'd you get that
And
from?
goats.
Yeah.
Yeah. So here's why you're the 0.899, right?
Yeah.
Yeah. So it says 30 grams of aluminum. So now if you guys look on the back, there's a whole chart here of other metals and other substances, what the specific heat is of the substances. That's where we get the 0.899. You can't use 4.18 for aluminum because that's for water, right? Specific heat is unique to the substance. That has a lot to do with force of attraction, how close particles are together. So aluminum, look, 0.899, very low. Why? It's a metal, and particles are really close together. That does have something to do with that. I didn't mention that earlier. Think about it. If water's forces are stronger than acetone, they're going to be a little closer together. Acetone's a little further apart. So if you look at steam, steam's specific heat is 2.01. Makes sense. Particles are far apart. How are they going to transfer heat to each other if they're far apart? So the closer the particles are packed together, the better they conduct heat. That's the smaller the number. So that may help you understand too a little bit. So anyways, multiply those 3. Who did I just talk to? Mariana, what'd you get?
539.4.
539.4 joules. Good. Good job. Questions on 1 and 7. Notice how, water has a bigger mass, but it's not much bigger. This number is the same, 20. This number is way bigger. It takes a lot more energy because of that specific heat. That's what I'm trying to really get you to understand. Aluminum heats up very quickly because it has a low specific heat, so you need less joules. I forgot to look up like the joules in this banana. I want to say it's like 400 joules or something. But I want to try and help you understand what the heck is a joule. It's a unit of energy, but how much? What does that mean? The more dense the food, like a steak, has more joules than a banana. So the denser the food, the more the greater amount of energy your body will get. Just trying to help you understand a little bit, because these numbers sometimes are random. Like, what is a joule? What does that mean, right? Okay. And number 6. 6 was hard, sort of. Kind of tricky. Anybody think they know? Earl.
What did you do? Q equals MHV.
Very good. We use Q equals MHV. Yes. Q equals MHV because it's boiling. This is what we use for boiling. So we go Q equals the mass. Earl, what is that? 40, right?
Yeah.
40 grams times the heat of vaporization of water, which is on table B. And that is, Michaela, what's that number? Heat of vaporization for water on table B. Reference table B. Or actually, it might be on the back, too. Heat of vaporization for water.
They're two different numbers.
2257, yeah. The reference table is more accurate. I would go with 2260. That's from the reference table. But if you use 2257, that's okay. That's what's on your reference tables, table B. Earl, which one did you use?
Just use the one on that.
All right. Well, the answers are probably pretty close. Did anybody use this number? Go ahead. What'd you get?
9040
9040.
000.
Like that?
Yeah.
Okay.
I got 902.
Are you sure?
Yeah, the other one, if you use 2257, it was like 902 something.
Go ahead, Michaela. 902.
90280.
80.
Yeah.
Something's not adding up here. Is there a decimal point here somewhere? I have too many zeros, right? That makes more sense. Yeah. Okay. So, you're doing the rest of those for homework due Monday. But what I'm going to do now in our notes is use this example. Well, I'll use a different example. But what I want to do in our notes is an example of HV, an example of HF, and then one more example of this, and then that'll be it. But I'm going to go kind of quick, so I want to intro something new today, and then we'll pick up with it Monday. All right. So just don't forget on the homework, show your work and tell me if it's endo or exothermic. It tells you that in the directions. That's what that line is underneath the delta H. By the way, delta H and Q are basically the same thing. All right. So take out your notes. We did a sample problem real quick at the end of the period yesterday. It kind of ran out of time. So we're going to do 3 more right now. An HV problem, an HF problem, another Q equals MC delta T, and then we'll be done. You will have one more practice worksheet. I got it right here. You were going to do it this weekend, but this worksheet's going to be given to you Monday, due Tuesday. So you're going to have a lot of practice with this. So we're not going to like pound on it in class. So that's that. All right, here we go. So write this problem down. And wait a second, I'm sorry. Did we write the answer to yesterday's? I think we did it real quick. Let me just go through that again. So the sample problem from yesterday, someone, Laura Griffin, read me the problem here, or the setup. Q equals 25 times 4.18 times what? 60. Okay, so there was the setup for the problem yesterday, and Slade, what was the final answer?
6,270.
That?
70.
Of 70.
Yeah.
6,270 joules. Okay. All right. So I just wanted to make sure we had the right answer down for that. All right. So that was the one we went over yesterday. Okay. Okay. So now I'm gonna do 2 problems next to each other. One's yes. Oh yeah. Yeah. Do what you gotta do. The only thing you're gonna miss is some sample problems, and I'm gonna give the answers to that quiz I handed back. Okay. I'm gonna do that right at the end. All right, so I'm gonna give you 2 problems next to each other. One's gonna be using Q equals MHF. One's using Q equals MHV. We'll talk about the difference. Okay, so here we go. Here's the first problem. Calculate the number of joules. Needed to melt 10 grams of ice. That's it. And over here, calculate the number of joules needed to boil 10 grams of water. Oh, you know what? I did want to add something at the end there. 10 grams of water at 100 degrees Celsius. So this one is 10 grams of ice at 0 degrees Celsius. I just wanted to tell you the temperature because that's how the regents will word it. You got to practice as many questions as we can with the same wording because they try and trick you. There's a reason I'm doing both at the same time. Cassie, why can't we use Q equals MC delta T for these? Because it's changing phase. Great answer. Can you give me another reason? That's a great answer, but I'm going to take more. Because we're not supposed to. All right, that's fair. Can anyone else give me something? How do we know we're not supposed to use Q equals MC delta T besides the fact that these are phase changes, which means you're not using Q equals MC delta T? That's very good. That's good. If you know that, you're good to go. But I just want to say something else to make it obvious. Yeah, there's no change in temp. If there's no change in temperature, right, we're at 0. We're at 100. You're going to see Monday and Wednesday, because I'm actually not here Tuesday. I'm coming in late. But Monday and Wednesday, we're going to talk about something called a heating curve and a cooling curve. And this will make it all make sense. It'll all come together. But for now, understand when something is melting, the temperature stays constant. It doesn't change until it's done melting. When something's boiling, temperature stays constant. It doesn't change until it's done boiling. So that's how we know. Another reason, can't use Q equals MC delta T. So we use Q equals MHF, Q equals MHV. Maddie, set this one up for me, please. Q equals 10 grams. 330. Yeah, you know what? I'm going to put the units in here just to show you. Very good. If you have joules per gram times grams, what cancels? Grams, because really it's grams times joules over grams, right? Grams cancel. So I just like to go over units sometimes. That's important, especially down the road. So you get joules. So you get 3340 joules, 3,340 joules. Questions? Hardest part about this is knowing what equation to use. Right now it might be easy because we're doing it right now, right? And I've said this. But picture yourself in June. You're taking, you took 70 questions already. You did 70 questions. This is question 71, the short answer question. You read it, you're like, wait, I know it's heat, but I don't remember which one to use. That's where you kind of have to remember these little tricks. Phase changes are for our MHV or MHF. That's if you can remember that, that's great. And then, more importantly, I think sometimes it makes it really obvious. If you're not given two temperatures, you can't use Q equals MC delta T. So unfortunately, there is part memorization here. HF is for melting. Melting and freezing, HF. So that's why we use that. Over here, vaporizing is kind of like boiling. So that's how we know to use that. Who can set this one up for me? Go ahead, Shane.
Q equals 10 times 200, or 2,251, or that.
This one because it's from the reference tables. So if you didn't, that's okay. But use the reference tables from now on just because that's what you're going to have on tests in the regents and stuff. So that's 22600 joules. All right. Here's the next question. We're actually not going to do another one. We probably don't have time, but your homework's good enough anyway. So we're just going to end with these, and I'll talk about the quiz. Why is this number so much bigger than this number? That's 22,000. This is 3,000. And this is something we're going to write in our notes. Max. I think what you said was it took more energy. It takes more energy to boil than to melt. Yes, but why? More what? More entropy. We're getting there. You're breaking something when you boil. You're not breaking it when you melt. You're only weakening it. Forces of attraction. So I want you to put this in your notes. It takes much more. Is someone going to go with you? Yeah, you guys can go. You can get this later or something. So yeah, just don't forget that worksheet's due Monday. It takes much more energy to boil. I'm going to put in parentheses HV. And to melt, that's HF, because forces of attraction are being broken, not just weakened. That's a really important concept. That's the kind of stuff that gets you 90s on Regents exams. If you understand why something is boiling at a higher temperature or melting at a lower, or really understanding a number and a concept, that's better than just typing in a calculator and getting an answer, right? That doesn't really do anything. So that's good. And we are basically out of time, so I will give you those answers on Monday to that quiz. And that's it. Don't forget the bookwork. Don't forget the worksheet. And have a good weekend.